if you're having a same, then hopefully that helps you feel better. So, okay, and we have okay, good, almost everyone here. Okay, we're recording. Good. Okay. Before I get into today's material, I want to have a little quick aside about orthogonal matrices. Okay, and actually, this is based on something that came up in a meeting with a student, where afterwards I realized I might have said something that was incorrect or could have been interpreted as something incorrect, and I wanted to make sure that for everyone here I have it laid out correctly. Let's suppose that Q be a 2x2 orthogonal matrix. An example of that would be a Gibbs rotation. Then Q has one of two possible forms. So in a 2x2 case, it's actually possible to characterize all orthogonal matrices. So one form is one that we are familiar with from Gibbs rotations. Oops. And that'll be C minus S S C. Where C is cosine and S is sine, so of some theta. Okay, and the first form, I'll type out the second one in a moment, is a rotation through the angle theta. And okay. I remember when I first presented this in class, talking about Gibbs rotations, I'd initially stated the wrong direction of rotation because I can never remember. So I'm going to tell you how I keep it straight. At like it's in the minus, whether it's clockwise or counterclockwise. So if you imagine, so what I do is I focus on the second column because that's where the minus is, and because the second column is what you get when you rotate to point 0, 1, because that's the second column of identity. So 0 in the first position, 1 in the second position. So if I take the point x is 0, y is 1, so it's pointing up the positive y-axis, and then I rotate that, then that means that the x-coordinate is going to be negative. So if you have a point that's a y-axis and you're rotating it to cause the x value to become negative, that means it's going to the left. In other words, it is a counterclockwise rotation. And then for orthogonal matrix, the inverse is a transpose. So if I take the transpose of this to get the inverse, the minus goes down here, and therefore that would be rotating in the opposite direction. It would be a clockwise rotation. Okay. Now. Okay. And yes, I really was going back to the book. Oh, good, everybody's here now, and checking that what I said is again correct, and yes, it is. So that's the first form of a orthogonal matrix of one we've seen. The other possibility is very similar. All I do is I negate the second column. So now the diagonal entries have opposite signs, The off-diagonal entries have the same sign. So what does this do geometrically? Is a reflection followed by a rotation. Because what I can do is I can take this second matrix and factor it. Whoops, that's way too many Q's. Okay, because this matrix multiplying on the right just negates the second column. So this matrix is the exact same rotation that we have over here. So we're multiplying this by some vector. What the vector will do is it'll negate the y coordinates only, and then carry out the same counterclockwise rotation through theta. So so let's have everything written out here. So the second form is a reflection. When you're negating the y coordinates, it's reflecting across the x-axis. Okay, so any 2 by 2 orthogonal matrix can be broken down into, can be characterized as this form or this form, because you're dealing with a trig identity, cosine squared plus sine squared equals 1, and what okay, and you have a choice when determining the entries of your orthogonal matrix to take either a positive or negative square root. So based on these choices of negating things, or choosing a plus or minus, that leads to these two different options. Yeah. It's also worth mentioning that the first form, if I take the determinant of this matrix, I get c squared plus s squared, which is equal to 1. Whoops. But for the second form, well, the determinant of this matrix is minus 1, and this is determinant 1. Okay. Because for all orthogonal matrices, we have the following. 1 would be equal to determinant of identity, which is also Q transpose Q. But determinant of a product is the product of determinants. The determinant of a transpose is the same as the determinant of the original. So this tells you right there, determinant of any orthogonal matrix has to be plus or minus 1. So these are the two possibilities. Okay. So we were dealing with only these for given rotations, but I want to make clear that we have both possibilities. And the fact is, this covers householder, because remember, a householder matrix is a householder reflection. So so just for fun, I'm going to form has this form. So I'll call it H is identity minus 2 VV transpose. All right, so that'd be, hold on, identity, whoops, forgot to break the line, minus 2 VV transpose. That's an outer product. And this is a good opportunity to recall what an outer product looks like. It's all possible products of individual entries of a vector you're taking the outer product of. Oops, so that'd be v1 squared. And then I'd have v1, v2, and then v2, v1, and v2 squared. Okay. So then I work this out. And what we have is, okay, so 1 minus 2 v1 squared. And then I have minus 2 v1 v2. And then down below I have minus 2 v2 v1. And then 1 minus 2 v2 squared. Okay. Now, keep in mind the vector v is a unit vector. It has a norm of 1. So we can think of v as a vector that has whose elements are a cosine-sine pair. Okay. Okay. So if I take it into account, what H looks like, it'll be easier to see by acknowledging the trig. Okay. So V1, that's the cosine squared. Here we have cosine and sine. Here again we have cosine and sine. And here I have sine squared. Now, but sine squared, if we keep in mind that sine squared is 1 minus cosine squared. Okay. So then I simplify this. So I get 1 minus 2 plus 2c squared. So after I simplify all of this, the two diagonal entries are just the negatives of each other, like we see here in the case of a reflection followed by rotation. Now, a reflection across the y-axis followed by rotation, you can think of it as it is reflection across a different axis, which is what a household reflection is, as I described to you back then. So if you were to work out the determinant of this, keep in mind that c squared plus s squared equals 1, you would get minus 1 for a determinant. Okay, now let's see if anybody remembers their trig. Can anyone tell me these expressions here, 1 minus 2c squared, and also 2cs, forget about the minus. What trig identities are described here? Like 2 cosine theta sine theta. What's that a trig identity for? Or 1 minus 2 cosine squared theta. What's that a trig identity for? We might not have anybody here who's taught trig, but you will someday.
Is it the double angles?
Yes, they're both a double angle. So the off-diagonal entries have a double angle formula for sine. All right, so if I write it out that way, Okay. Then in the 1, 1 spot, we have cosine of 2 theta. And then I have minus sine 2 theta. And then minus 2 sine, minus sine 2 theta here. And then minus cosine 2 theta. So, okay, something weird happened here. I'm not sure why this one is black instead of blue. Okay. I don't know. Okay. So once again, so this matrix is of this form, where you have the diagonal entries negatives of each other if the off-diagonal entries are the same. So in fact, I could write this as sine of minus 2 theta because sine is an odd function. So in fact, yeah, if I do that. Okay. Okay. So I could think of it that way, and then it fits this form exactly for whatever angle 2 theta here. So we can see that Gibbons rotations fit the first form, household reflections fit the second form. All right. Any questions about what happened here? All right. Now, 2 by 2 household reflections might not be all that useful, but if you have an n by n orthogonal matrix, you could represent it as a product of rotations or reflections, because what you're doing is, like, if you're picking 2 rows or 2 columns and performing a rotation reflection on them, orthogonal matrix of any size can be described as a product of these kinds of operations. Okay. All right. So now I just wanted to put that out there for all the different kinds of orthogonal matrices that we can have. And now I can finally, 25 minutes in, get into what I intended to cover in the first place. So we'll see how this goes. The singular value decomposition, well, it's something I never heard of when I was an undergrad. Became a big deal when I was a student at Stanford, because a director of a scientific computing program there, and who would eventually be my advisor, Gene Golub, the main achievement of his career was coming up with the first practical algorithm for computing this new matrix, matrix factorization of a singular value decomposition that is very useful for a lot of things, particularly least squares problems. And in fact, because really, he was so closely associated with the singular value decomposition, or SVD, that I remember the first time I went to his house for like a get together, everybody, and his license plate was Dr. SVD, and then later when he got a new car, his license plate was Prof. SVD. So basically, singular decomposition was his thing. And in fact, I still won't be able to show you the algorithm for the SVD yet. I'll be able to tell you about the SVD's properties, its applications, but toward the end of the semester, I'll be able to show you the algorithm once we learn about eigenvalues, eigenvalue methods. Okay, so, all right, and we're going to see it has a whole lot of uses. It may be expensive to compute it, but once you have it, you have so much valuable information that you can get from it. Okay, so I need to show you that it exists, show you properties that it has, and what it's used for. Okay. In fact, household reflections are going to help show its existence. Okay. So I'm going to use a matrix 2 norm to help me do this. So I'm going to assume that x is a unit vector in a 2 norm sense. So the 2 norm of x is 1. And it's not just any vector, it's a vector so that if I compute a times x, this is a vector norm, happens to be equal to the matrix 2 norm of A. And how do I know that such a vector exists? It's because the definition of an induced matrix norm, which I will recall here, the matrix 2 norm is defined to be the maximum over all unit vectors, again in the 2 norm sense, of the vector 2 norm of A times x. So there's some vector x that we can fill in here at which this maximum is achieved. So that, and that's what we would get for this x. Okay. All right. So now what I'm going to do, I'm going to define a vector z to be A times x, and then normalize it to get a unit vector y. So then I have this. A times x, which is z, is equal to sigma times y, where sigma is the 2 norm. So all I'm doing here is the sigma y basically separates z into its magnitude, which is sigma, which is also the 2 norm of z, and its direction, which is y. Okay. Okay, so okay, so that's where this comes from. So all of these things that are all equal to sigma. So A times x is equal to the norm of A times some vector y. That's a unit vector. Okay. Now I'm going to use householder reflections, because I can come up with a householder reflection that will take x and zero out all the entries except the first. So this is exactly the same usage of householder that is we needed for the QR factorization, because there we're trying to zero out all the entries of a column except for the first one. And the thing is, remember, what goes here has to be a unit as the same norm as x. Well, this is a unit vector, but x is a unit vector, so that works. Same thing here with y. Y is a unit vector, so a householder reflection applied to y will also give me a unit vector. So this is a householder reflection that will zero out all the elements of y except for the first one. Okay. One of the homework problems, I believe I don't think I assigned this one. let's see. No, I did not. This problem is about if you have any vector, you can, that's a unit vector, then you can, or actually any two unit vectors, you can find a household reflection that maps one to the other. As long as they have the same magnitude, like for instance, for both unit vectors, then that's possible. Using the approach that I showed in class. And in that case, I was dealing with a multiple of E1, but it can be done with any vector over here, as long as the two vectors, the input vector x and the output vector here, have the same magnitude, because you're multiplying by a orthogonal matrix, which always preserves magnitude. So now, what happens if I use both of these household reflections in combination? So, so what I need to use here is the fact that we're using a property that a household reflection is its own inverse. So that would tell us that, for example, okay, V1 E1 is equal to X. And similarly, U1 E1 is equal to Y. So these relationships that we have here, I can put the matrix on either side of it, and it works because a household reflection is on inverse. Because really what I'm doing is I could take this equation, multiply both sides by V1 inverse, and I have V1 inverse over here. But V1 inverse is V1. So that's why I can do this. And that's what I'm using down here. I started with, I'll put a parentheses here. I'm computing this. V1 E1 is X. So now I have A times X. But A times X is equal to sigma times Y that I'm using down here. Remember, sigma is a number, so I can put it wherever I want. And then I have U1 transpose Y. But remember, a householder reflection is symmetric. So that's the same as U1 Y. I forgot the sigma. So then we get sigma times E1. And similar down here, if I take this expression, which is almost the same one I started with, but I have an E1 transpose on the left instead of E1 on the right. Well, that would be the same as, dang it, U1, stop that, U1 E1 transpose A V1. Okay. So here I'm using the fact that a transpose of a product is a product of a transpose is in reverse order. But U1 E1 is Y. So Y goes here. Now, I'd like to simplify this. I can do a little more with it, because that's the same as A transpose Y transpose V1. Again, using the same property of transposes. But the problem is, right now, I don't really know anything about this vector. So before I go any further, I need to see what's going on with this in terms of norms and such. Now, are there any questions up to this point? I know I've done a lot of manipulations. Okay. That was an unfortunate notation choice here. Here I have I defined Z to be A transpose Y. This is not the same Z as up here. It's just that this Z, I didn't need it anymore. So I'm reusing a letter. So I should have used something else, but okay. At some point, you just run out of letters. Okay. So if Z is A transpose Y, I can write Z as a unique decomposition of the vector linear combination of vector X and a vector W that is orthogonal to X. And I'm assuming that X is known to be a unit vector. W we're going to assume is also a unit vector. And X and W are orthogonal. Now, this is something you actually learn in your introductory linear algebra class when you're covering what's called projection. That any vector can be uniquely decomposed into the sum of some vector plus another vector that's orthogonal to it, where this is like the best approximation of its vector in this direction. So this is like a projection of Z onto X, and this is the remainder of it. And these two are orthogonal. Okay. So I'm just making use of that. So what can I do with that? Since X and W are orthogonal, to figure out C, I could just take the inner product with X. Actually, the same thing's going on in PDEs, where we multiply by functions and integrate. That's the inner product to get coefficients. It's exactly the same principle at work here. That's what I point that out for those of you who are in PDEs, so that you can make note that this is the same principle in effect. So if I take the inner product of both sides of this with X, okay, I'll just write out what that is. X transpose Z is equal to C X transpose X plus D X transpose W. Okay. So that's what I get from taking the inner product of both sides of this with X. Well, X transpose X is 1 because X is a unit vector. X transpose W is 0 because of this. So this term goes away, and C is the only thing that's left here. So C is X transpose Z. But Z is equal to A transpose Y. And using the properties of transposes, that can be rewritten as AX transpose Y. But from what I have up above, stop it, AX is sigma Y. So if I fill that in, now I have that. But Y is a unit vector. So this is 1, so we have sigma. So in other words, C is equal to sigma. That's what I wanted from all of that. Okay. Now the 2 norm of this vector, these vectors are orthogonal. So so from this equation, the 2 norm of Z squared is equal to but look at how Z is defined. C, which is sigma X plus dW. Now, using the properties of inner products, because this is the inner product of its vector of itself, what I get is sigma squared X 2 norm squared plus 2 sigma D inner product of X and W plus D squared 2 norm of W squared. So this is what we get when we expand the 2 norm squared of a sum. We get this. But this is 1. This is 1. And that's 0. So it boils down to this. We just have sigma squared plus D squared. Now, what I can do with that, we're getting there, I promise. Here I'm using a fact that I haven't really shown yet. It's actually from a homework problem, another homework problem that I did not assign. The 2 norm of A is equal to the 2 norm of a transpose. This actually comes from a homework problem that I did assign, where you show that the eigenvalues of AA transpose are equal to the eigenvalues of A transpose A. That can be used to quickly show this. Now, how does that help me? Well, okay, so sigma squared plus D squared, that's the 2 norm of this vector squared. But using properties of norms that you would have used in homework, this is less than or equal to norm of A transpose times norm of Y, all squared. But the norm of Y is 1. So I'm just left with a 2 norm of A transpose squared. But the 2 norm of A transpose is a 2 norm of A, which is, stop it, sigma. So what I'm saying here, sigma squared plus D squared is less than or equal to sigma squared. Well, what can I conclude from that? So if sigma squared plus D squared is less than or equal to sigma squared, what does that tell me about D?
It's larger than sigma squared.
No.
It's less than or equal to 0.
Yeah, the only way this can happen is for D to be 0, because this term I'm adding on, plus D squared, that's going to be positive. If D was non-zero at all, this would be larger than sigma squared, which is a contradiction. Okay. Now, what I got from all of this was A transpose Y is sigma X. So now I have these two relationships. AX is sigma Y. A transpose Y is sigma X. Now, what do I get from that? Well, before I was working with this, and I'd gotten down to this point, A transpose Y transpose V1, but I didn't know what this was yet. But now I'm back down here. Okay, so if I fill in the step that I had before, which is A transpose Y transpose V1, okay, But A transpose Y is sigma X. So now I fill that in here. But that's the same as V1 transpose X, the whole thing transpose. But V1 is its own inverse. Well, it is its own inverse. It's also its own transpose. And from what we have up above, V1X is E1. So now I have E1 transpose. Okay, now if I put together most important things I got from all this, that U1 transpose AV1 multiply with E1, that was figured out earlier. That is sigma E1. And now we also have this relationship. And that turned out to be sigma E1 transpose. Now, what on earth am I doing here? So, we're interested in the structure of this matrix. And what we have just learned is that if I take this matrix, U1 transpose AV1, and take the first column, then that first column has a sigma in the first position, everything else 0. Now I take the same matrix, U1 transpose AV1, and by multiplying by E1 transpose on the left, I'm looking at the first row. The first row of this matrix also has sigma in the first position, and everything else in that row is 0. Now, why is that really huge? Because it means that this matrix has this structure. Sigma up here all by itself, zeros here, zeros here. In other words, it's a block diagonalization because I have 0 here and here. So this is the start of reducing A to diagonal form. So what I could do is everything I just did with A, I can now repeat with A1. If I were to keep going with that and I keep getting a matrix that's closer and closer to diagonal form over here by piling on more household reflections on the right and household reflections on the left, and I get this. U transpose AV is a diagonal matrix, sigma. So U and V are orthogonal. U is m by m, V is n by n. So A is not necessarily a square matrix, it's some m by n matrix, any size. Sigma is a diagonal matrix with values sigma 1, sigma 2, etc., all along a diagonal. And however many you have is a minimum of m and n, basically whatever will fit in the matrix. Okay, and yes, so it's the diagonal matrix. All the off-diagonal entries are 0. What we can also say is that the diagonal entries are ordered. So sigma 1 is the largest, and it keeps going down from there. And the reason for that is, if I take A and then I whittle it down to matrix A1 that is smaller, the 2 norm of this has to be less than or equal to the 2 norm of the original. So if I were to keep going, the sigmas I'd be getting on a diagonal are at least non-increasing. So that is the singular value decomposition. A is U sigma V transpose. So this is how it's typically written. And you can get the SVD of a matrix in MATLAB by using a SVD function. And so its usage would be something like this. USV is equal to SVD of A. Okay. So then you would get the three parts, U, sigma, and then V that's transposed over here. Okay. So now I've spent way too much time, most of the class period, just showing you that the SVD exists, which is not really very closely related to the algorithm for it. I need to talk about its properties. Unfortunately, I might not have time for everything. That's unfortunate, but I guess I'll deal. Okay, so these diagonal entries, the sigmas, diagonal entries of sigma, those are called the singular values. The columns of U, U1 up to UM, those are the left singular vectors, because U goes on the left. And then these are the right singular vectors, the columns of V. Now, how the left and right singular vectors are related, if I multiply A by a right singular vector, I get a left singular vector times the corresponding singular value. Similarly, if I multiply a left singular vector by A transpose, I get the corresponding right singular vector with the corresponding singular value. This notation is meant to refer to singular values in order. So sigma 1's the largest, sigma 2's the second largest, and so forth. And if it's not clear what matrix we're talking about, then we put A in parentheses after it. But if we're only talking about one matrix, then we just use sigma I. And this notation is used to refer to the largest and smallest singular values because those are quite useful, as we'll see. Okay. So what can singular values decomposition tell us about A and systems of equations involving A? Well, the rank of A is the number of non-zero singular values. Also, if R is a rank, then the first R columns of U, the first R left singular vectors, those are orthonormal bases for a range of A. And then if you start after the rank, so VR plus 1 up to Vn, so the last right singular vectors, those describe the null space of A. So the singular value decomposition gives us very nice orthonormal descriptions of a range and null space of A. Okay. Now, because R is a number of non-zero singular values, I can write A this way as a sum of R terms involving singular value, left singular vector, and then right singular vector transpose. This just comes from the perspective of matrix multiplication as a sum of outer products. Is that we only need R terms because that's how many non-zero singular values you have. So this is called the Svd expansion of A. So this leads to what is called an economy size SVD, just like we have an economy size QR. So I can write A this way. Okay. I should have a. Okay. So what I could do is I can let U1 be the first n columns. And then I have sigma 1's an n by n matrix instead of m by n. And then this V is still the same one. Okay. And this is particularly helpful if A is full column rank, that we can write it this way. I'll show you an example involving a specific matrix. All right, so here's a given matrix A. And if I compute the singular value decomposition, here's U and V, orthogonal matrices, and the singular values are here. So this is S or sigma. Oh, that should be a sigma. Great, never a mistake in the book. Stop it. Oh, this thing's aggravating sometimes. Okay. Okay. So here we have a singular value being 0. We only have these two non-zero singular values. So what we can conclude from that, if I use these column partitions of U and V, or U1, U2, U3 are the columns of U, and similar for V. So the rank is 2. And the range, therefore, would be just the span of the first two columns of U. And the null space comes from a third column of V. So now I can write U this way, using first singular value U1 V1 transpose plus second singular value U2 V2 transpose. U3 and V3 play no role because of this singular value being 0. Okay. So if you have whatever the rank of a matrix is, you can use that many terms, that many outer products to describe a matrix completely. Okay. Now the SVD is also helpful when it comes to certain norms, the 2 norm and also the Frobenius norm. For one thing, the largest singular value is the matrix 2 norm of A. The Frobenius norm of A is a square root of sum of squares of all the entries of A, but that's also equal to the sum of square root of sum of squares of all the non-zero singular values. Notice this tells you that the Frobenius norm is always greater than or equal to the 2 norm. Okay. We also have a characterization of the smallest singular value. So if you consider all non-zero vectors x, and you look at the smallest value of this expression, or simply the minimum of this expression here, that will be the smallest singular value of A. Okay. There are some problems in the book, I don't believe I assigned them, where you show that if I take a matrix A and multiply on the left or right by an orthogonal matrix, it does not change the 2 norm, and it does not change the Frobenius norm either. And so it's because these norms it says they're invariant under orthogonal transformations. In other words, multiplying by an orthogonal matrix on either side. Once you have that, that makes it easy to prove these. Because basically it reduces the 2 norm or Frobenius norm of A to the 2 norm or Frobenius norm of sigma a diagonal matrix. So it's a whole lot easier to compute. Another thing we get from the SVD, very simple formula for the condition number of a matrix A in the 2 norm. It's equal to the largest singular value divided by the smallest. Now, if A is invertible, then this small singular value will be non-zero. Now, if A is not a square invertible matrix, you can look at the largest and smallest non-zero singular values and get an idea of what the condition number would be. Like that's what we did in the full rank least squares problem. So if a matrix A is full column rank, it may not be invertible, but all of its singular values are non-zero. So this formula would still apply, even though there wouldn't really be an inverse per se. All right. Now, some applications of the SVD for least squares. Okay, so suppose I have a least squares problem where here I'm not assuming anything about the size of A. So this could be an overdetermined or underdetermined system. But I'm trying to minimize the residual norm, B minus AX. Now, I can use the SVD to help me do this. So if I look at B minus AX, 2 norm squared. So here I'm just filling in the SVD of A. Sorry, I should have made it bigger a long time ago. Okay. Now, if I keep working on this, I can multiply this by U transpose on the left. That's an orthogonal matrix, so it does not change the 2 norm. So that would cancel out the U here. Now, for convenience, I'm going to let C be U transpose B, and then V transpose X I'm going to refer to as Y. So now I have this much simpler expression involving a diagonal matrix sigma. So now I can write that out element by element, because here I can literally take the elements of this vector. So C1 minus sigma 1 Y1 is the first element of this vector, and then so on until we get to element R, because here's where we have non-zero singular values. And then I keep going the rest of the components of C. But here I'm not subtracting off a sigma times a Y, because after R, the sigmas are 0. So I just have that. So the thing is, I want to make this as small as possible. So since it's a sum of squares, to make a sum of squares as small as possible, you want to make, if you can make any elements equal to 0, then that's what you want to do. So to minimize this, I can set each Y, because Y is my unknown. It's related to X, my solution. So I can choose Y to make each one of these equal to 0. Now these I can't do anything about because C is given, because it comes from multiplying a given vector B by U transpose. So these I have to let go, but these I can make 0. So what that means is, keep in mind, Y is an N vector, but I'm only setting the first R elements. So to make this minimum, I can set the other elements of Y from R plus 1 on up. They can be anything. That's because they don't have any effect on this expression. Therefore, they don't affect this either. So what that tells me is if a rank of A is less than n, so in other words, R is strictly less than n, then I have infinitely many solutions because I have a bunch of y's that I'm able to set to whatever I want. So what I could do, though, if I want to pick out a unique solution, I can set my goal to minimize the 2 norm of x and therefore also y. So I can just set these to 0. So that gives me a unique solution where it minimizes b minus ax, but it also minimizes the 2 norm of x. So putting everything together, what is my least square solution? Well, x is vy because of this, but v, all right, okay. What is y? We get y by dividing certain elements of C by corresponding singular values. That's the same as multiplying by this matrix sigma plus, which I now need to define. It's a matrix you get by taking sigma and taking reciprocals of all the non-zero singular values. Everything else that was 0 before remains 0. So that's how I define sigma plus. And then I have C, which is defined to be U transpose B. So I fill that in here. So this matrix, V sigma plus U transpose, I call A plus. And that matrix is defined to be this. That's a definition of a pseudo inverse of A. It's also called the Moore-Penrose inverse. The pseudo inverse is used to define the concept of an inverse for a matrix that doesn't actually have an inverse. Now, if a matrix A is invertible, then the regular inverse and pseudo inverse are the same. But when A is not invertible, this basically comes as close as you can get to having an inverse. Because in a regular inverse, you have all non-zero singular values, and you must take a reciprocals in the inverse. So in fact, it would be V sigma inverse U transpose. It's the same structure. But when that's not possible, then you just flip the non-zero singular values and leave everything else as 0. So just as if A is squared invertible, the solution of Ax equals B is x equals A inverse B. If it's a least squares problem, then your solution is x is pseudo inverse of A times B. So that way we have a uniform definition of solutions to square Ax equals B systems and also least squares problems, whether they come from overdetermined or underdetermined systems. Now, we have an easy way to get the pseudo inverse in Matlab. Now, inv, just plain old inv, lets you get the inverse. Pinv gives you the pseudo inverse. But it's not a good idea to compute the inverse of a matrix explicitly. So generally, we would not need a pseudo inverse explicitly either. But if you really need that, then here's how you can get it. By the way, I think I never really discussed why it's impractical to get the inverse of a square invertible matrix explicitly. Forming A inverse explicitly costs, whoops, (8/3 n cubed operations, 4 times the amount of just doing Gaussian elimination and back substitution to solve a system, because you never want to solve as AX equals B by computing A inverse, and then you could multiply A inverse with B. Because if you just use a regular method that I showed you in chapter 3, that's 2/3 n cubed floating point operations. But if you go to the trouble to form A inverse and then do a multiplication of B, that costs you a whole lot more. So don't do it. And similarly, the pseudo inverse, bad idea to form explicitly. Okay. Now, you actually don't need a pseudo inverse in Matlab to get the least squares solution. You can use a backslash operator. So a backslash operator figures out what kind of problem you're trying to solve. If A is squared invertible, then it'll do Gaussian elimination, partial pivoting, and forward and back substitution to solve a system. If it detects that like A is rectangular, it'll solve a least squares problem. If it's an underdetermined system, it'll give you a minimum norm least square solution. In the case where AX equals B has, or minimizing AX minus B has infinitely many solutions, it'll pick out the one as minimum norm. So backslash will do all of that for you. It's quite versatile that way. I just realized that I'm about to run out of time. I want to see what I have left here. I don't think it's very much, or I hope not anyway. Oh. Yeah, I need to take a look at what is on tap for Monday. Oh, least squares linear constraints. Okay. All right. It'll be fine. So this low rank approximations, I will pick up with that on Monday. And I have to promise not to do any digression into something else like I did at the start of today when I talk about different kinds of orthogonal matrices. So I'll cover the last of low rank approximation, like SVD applications, and then let's see. Yeah, for the next section about least squares of linear constraints, I only assigned one problem on that, so I'll just make sure you're able to do that problem. Okay, so well, my next class starts in 16 minutes, so I will end actual class now. But if anyone has homework questions, then they're welcome to stick around and ask, or of course they can also contact me later, as I'm sure many of you do. Okay, so well, doesn't have anyone any questions since we have 1 minute left. People are leaving, so okay, I'll stop recording now.